Okay, so here's a problem. We're going to draw the influence line for, well, let's see what the problem says first. It says determine the maximum positive moment that can be developed at D. So since we're asking for moment at a particular point, that probably means we're going to draw an influence line. And you'll also notice that it's got a live concentrated force, a live uniform load. We really haven't talked about what that means. And then we'll have a dead uniform load. So we've got 3 different loads that we want to position. But we want to find the moment at D. So I need to draw the influence line for the moment at D to get started. So let me go ahead and, using Mueller-Breslau, we should be able to sketch the shape of this moment or this influence line pretty fast. So let me kind of bring down these points kind of as a template just to get started. So let's go back and remember what Mueller-Breslau says is you go to D, kind of imagine that you have a hinge, right? Can't hold the moment. And then we apply positive moment to both sides. So what's going to happen to point D? Is it going to move up or move down? It's probably going to move up. So I'll draw it, say it's there. Well, because it moves up and that's a hinge, we'll get a linear portion here from E to D. You'll notice this segment BCD will kind of seesaw over C. And then the hinge at B, we'll let it rotate back up, and then we can connect back to A. So there's the shape of my influence line. Everybody see that? Any questions about that? So now the point we need to do is decide what case are we going to apply to actually find a value. If I can find, say, this value, then I know by similar triangles that this value will be what? Same. Both these lengths here are 5 feet. So if I find any one of these peak values, you can see it's going to be the same value. I think the easiest one is going to be to find the moment at D when the unit load is at D. So let me redraw the problem with that under consideration. So there's this is from A to B, and then B to C to D to E. So we have a pin connection at A. There's my hinge at B, a roller support at C, and then another roller at E. So that's the geometry. And since I'm interested in this point, that means my unit load is over D, which will be right here. So that's the problem I need to solve. So let me just write this up here. So this is A, B, C, that's point D and E. So it's the same problem, except now I've located the unit load at D, which should give me this value on the influence line. So I need to find the internal moment at D for this position. So what I want to do is I'm going to draw a free body diagram. I'm going to break this up into 2 pieces. So I'll have A to B, and I'm going to assume at A that I have a force in the Y direction and one in the X. That's a pin. And then at B, that's a hinge, right? I'm going to assume also that I have a force BY and BX. Well, on the other free body from C, D to E, these are going to be equal and opposite. And then I'll have the rest of my structure. So B to C to D to E. So at C, it's a roller, so I'll have a reaction, CY. And over here at E, I'll have a reaction, EY. And then don't forget my unit load is here at D. So let me put some dimensions on here. This is 5 feet, 5 feet, 10 feet, and this is 5 feet. So there's A to B, and there's B to E. You see that? Now, ultimately, I want to cut the structure here and find the internal moment at D. So when I do that, let me just let my pen be the cut. Do you want to work the right side or the left side? Looks like the right side is going to be easier. So that means all I need is what? EY. How can I find EY easily? Well, there's no load on this section, right? So the free body diagram from A to B, what are the forces equal to? They're all 0, right? By is 0, Bx is 0, everything's 0. There's no force. So that means that By and Bx here are also 0. So that means the only thing I don't know is Cy and Ey. So how can I find Ey easily? Some moments at C. So if I sum moments at C, set equal to 0, this force is creating a negative moment with a moment arm of 5. Ey is creating a positive moment with a moment arm of 15. So Ey is equal to, what is that, 1/3? 5 divided by 15? Everybody see that? So then all I do is cut the structure at D. I now know that Ey is 1/3, and I now have the thing I'm looking for, the moment at D. Now I will go ahead and put in that, yeah, my unit load is right there, but you'll notice it creates no moment about D because it's acting on D. And this has a length of 10. So what's the internal moment at D? Well, some moments at the cut equal to 0. And what do I have? I have the internal moment, which with my sign convention is negative. I have Ey, which creates positive moment with a force of 1/3 and a distance of 10 feet. So the moment at D is equal to 10/3 feet. I know it's kind of odd that it moments in feet, but remember, the force component has no unit.
Are we able to assume that AY, BY was 0?
Well, if you look at this free body diagram, let's say right here, this is the one to the left, right? If I sum moments at A, what do I have? The only thing that creates moment about A is By. So By has to be 0. Plus, look at this. There's no force on it. We don't usually have any reactions when it's not loaded. So now I know that this position is 10/3. So what's this value? Negative 10/3. So I've done my influence line. So now I can solve the problem. The problem is, what's the maximum positive moment produced by these three? So when I'm talking about positive, I want to deal with the positive values, right? So if we start with the concentrated force, which is live, which means it's moving around, what position on the beam will it create the largest positive moment? The largest positive value, actually at D, right? So that means that component is going to be the magnitude of the force, which is 4 kips, times the value there, which is 10/3 feet. So it looks like I get 40 thirds, which is 13.33. Is that right? Oh, is that right? Yeah, that's right, isn't it? 13.33, and that will be in kip feet. So that's the contribution from the concentrated force. Now we've done this one before. What about the dead load? The dead uniform load. Well, dead loads don't move around. They're fixed. So we're going to assume that the dead load is applied throughout the entire structure. So how do we handle a distributed load, or a uniform distributed load, with our influence line? We have to take what? The area under the curve. There's going to be some positive area, and there's going to be some negative area. We have to add it all up. So if I look at my uniform dead load, it's 200 pounds per foot. I'm going to go ahead and convert that to kips. So that'll be 0.2 kips per foot. And then I'm going to find the area of this. So there's a 1/2, because it's a triangle, so it's going to be 1/2 base times height. So the first one, the base will be 10 feet, and the height will be negative 10/3 feet. And the second area will have a base of 15 feet and a height of positive 10/3. So that's the total area under the curve. 1/2 base times height for the negative section, 1/2 base times height for the positive section. So that's going to, I don't know what that's going to be. 25/3 divided by times 0.2. What's that? What anybody get for that? I'm just looking at this piece here. I've got 10 of those negative, and I got 15 of those positive, so that means I should have 5 times that positive. So that should be 50/3. 50 divided by 3 divided by 2 times 0.2. That's 10. 1.6? Anybody else get that? 1.6? Exactly 1.6? Lots of sixes. Okay, so let's say 1.67. How about that? And that'll be kip feet. Yes?
Do you take the area under the entire?
For the dead load, you do.
Okay.
You don't get any choice there. You have to take the whole area. So, depending on where the influence line works, even though I'm looking for the positive effect, the dead load might actually produce a negative number. If, say, this negative value was bigger than this positive area, so for the dead load, you'd get a negative value no matter what. Now, the next one is different. This is the live uniform load. So, oddly enough, it's a uniform load, but it's live, which means it can move around. So you get to decide where you want to put it. Now, since I'm trying to compute the biggest positive moment, I don't want to put it anywhere in the first 10 feet, because that's going to give me what? A negative influence. So I want to put it only from C to E and get all this positive area. So the live load has an intensity of 300 pounds or 0.3 kips per foot. And when I multiply it by the area of the influence line, I'm only considering the positive area. So the base of that area is 15 and the height is 10/3. So somebody compute that for me. 150 divided by 6 times 0.3, whatever that is.
4.5.
4.5? Anybody else get 4.5? Waiting for an affirmatory nod. Anybody?
I got 7.
You got 7.5?
Is that 10 over 3 or?
That's a 3.
Oh,
You did a 5?
yeah.
So it's 7.5?
Yes.
Thank you. So now the total moment at D will be the sum of these. So it looks like 22.5. Does that look right? This plus this is 15, right? And 15 plus that, it looks like 22.5. So 22.5 kip feet is the maximum moment at D produced by this set of loads. And just so you guys can see that, let me redraw the structure real quick. So here's our pin at A, and I have my hinge, and I have a roller at C, and then I have a roller out here at E. So let's see, first things first, the dead load. Remember, the dead load goes across the whole structure. So that's our dead load. The live load, I'm only running from C to E. And then where does the concentrated force go? At D. So that's the load combination for this particular one. The dead load runs the whole structure. The live load we position just over the positive area of the influence line. And then the uniform load, the concentrated force is at the largest positive value, which is right at D. I'll go ahead and put in these dimensions just to help you see it. Any questions about that? We'll do some more of these, so we'll get back to that. Okay.